Speaker. Hello, welcome to another NGINX event in our recent series of webinars. My name is Andrew, and I'm one of the co-founders of NGINX, the company. At NGINX, we've been working hard on a software that powers over 20% of the internet websites today. This software is the NGINX Web Server and Web Application Accelerator. NGINX was designed by Igor Sissoyev, the original author, with one single goal in mind: to make websites holistically faster. Whether you are an experienced user of NGINX or just started, I'm hoping you'll find this webinar useful and entertaining. And now allow me to introduce Owen Garrett to you. Owen is responsible for the product development and product marketing here at NGINX. Owen is now going to do a presentation and a demo on how NGINX could be used for load balancing. Owen?
Thanks, Andrew. Folks, thank you very much for joining us today on this webinar, where I will talk through how our users use NGINX to load balance and scale their web applications. Before I dive into the specifics of load balancing, I'd like to just run through a quick review, a background of what NGINX is. Andrew described it as a web server and a proxy. In fact, NGINX is a great many things. It's a software web engine that manages HTTP web transactions, and it can do a number of different things with them. NGINX can operate as a web server, receiving HTTP requests and responding to them directly from content on disk. It can operate as an application gateway, receiving web requests and then proxying them through to other protocols, applications that use protocols like FastCGI, WSCGI, or Passenger. And it can also operate as an HTTP proxy, receiving web traffic and then forwarding and load balancing it on to origin servers, what we often refer to as upstream servers. These upstream servers respond, and NGINX then delivers that response back to the remote client in the most efficient way possible. NGINX packs a lot of features into the software application. Features that improve the performance of applications, features that improve the security of applications, features that improve high availability, features to transform or manage the delivery and quality of service of traffic, and advanced features such as geolocation or mail delivery. NGINX powers about 140 million websites worldwide, based on March's Netcraft figures. And if you look at the busiest websites in the world, taking the top million from the Alexa traffic rank statistics, 22% of those websites run on NGINX. However, if you drill down into the very, very busiest of those sites like Netflix, and Pinterest, and Flickr, then 37% of the top 1,000 websites by traffic deliver their web content and their web applications through the NGINX web server and web proxy. The NGINX software is available in a couple of different forms. NGINX is a leading open source project hosted at NGINX.org with a very vibrant and active community contributing third-party modules to the core web server software. NGINX Inc., the company that was founded on the basis of the NGINX software, supports both NGINX.org, the open source product, and also a commercial product. And sales and the commercial product help to support the development of both the open source and commercial offerings. The commercial product, NGINX Plus, takes the key modules from the NGINX open source product, both the NGINX ones and some of the key third-party modules, and adds in some additional capabilities: advanced load balancing, features that make NGINX easier to manage and deploy in large enterprise environments, And very importantly to many of our customers, also adds in commercial support. This support is delivered from the same team, the same engineers who are responsible for the NGINX open source product. As I run through this presentation, some of the features that I highlight will be available in both the open source and the commercial product. Some of the features will be specific to NGINX Plus, the commercial product. So I'll make sure to highlight those out and call them out as we go through this presentation. Why should you load balance in the first place? I imagine for many of you, this will be very common knowledge. But as a quick review, there are broadly speaking 3 or 4 reasons why organizations use load balancers. Load balancers can improve the availability of applications by detecting failed servers and routing traffic away from them. They can improve the management of those applications, providing you with a way to take servers out of service, apply updates, apply security fixes without impacting the end user level of service. Load balancers can help you scale your applications, giving you more capacity by allowing you to scale the application infrastructure horizontally. And load balancers like NGINX can also help you with some advanced techniques such as A/B testing and application migration. Load balancers work in a variety of different ways. One of the first ways that applications were load balanced used a system called DNS round robin. A very, very simple system akin to putting several phone numbers for the same address in a phone book. When clients attempt to access a service using its DNS name, examples.com, DNS round robin will serve up one of several different IP addresses. The thinking behind DNS round robin is that you simply provide your service on several machines and you add the IPs for all of those machines into the DNS records. It's a good, cheap way to get started, but it fails to deliver on many of the benefits that I've mentioned. Application availability, it's very slow at responding if an application fails. Increasing capacity, it's not particularly scalable. So organizations then looked at layer 4 technologies, typically deployed within a hardware load balancer. Layer 4 load balancers are advanced network switches. They don't contain a full TCP stack. Rather, they stream TCP packets through the device, tracking the TCP session and pinning that to a target server. Many commercial hardware load balancers can operate in this fashion, and they deliver excellent performance, but they're somewhat limited in the kind of features that you can deploy. Without a full TCP stack, the device will struggle to modify TCP traffic to handle things like out of order or broken TCP packets. So over the last 5 to 6 years, the software load balancer has begun to predominate. Software load balancers are often referred to as reverse proxies. They're a software application running on top of a proprietary or standard TCP stack. NGINX is a great example of that, running on Linux or FreeBSD. It terminates TCP connections just as a web server would. It reads the HTTP request within that connection, and then it can apply transformations, modifications, and changes to that request. It then picks a target server, makes a new connection to that target server, or reuses a connection from its keep alive cache, and sends that request down to the target server. Receives the response. It may transform, rate limit, or otherwise change the response, and then delivers it back to the end user. These solutions give you the greatest degree of flexibility in customization, in capability, and in security. Another option you may have come across occasionally is a cloud-based solution. If you subscribe to services from Amazon Web Services or Rackspace, then you will have the option of using Amazon's Elastic Load Balancer or one of Rackspace's load balancing offerings, instead of deploying your own software load balancer on the cloud. Check the capabilities of those devices. They're generally capable and efficient, but they don't always provide the advanced features and facilities that I'll talk about in this session. And if you don't have a load balancer, if you don't scale your site correctly, if you don't have a means to detect application errors and route away from them, then unfortunately, this is the potential end result. So now I'm going to dive into 3 basic load balancing case studies using NGINX and NGINX Plus to deliver basic load balancing, to give you more control over how traffic is routed, and then at the end to talk about some advanced techniques that you can use. Basic load balancing is ideal when you simply need scalability for your application. It's delivered from several servers, all with the same capabilities, same applications, same services. They're more or less indistinguishable. And the job of NGINX is to load balance traffic across those services, first to detect and work around errors, but also for each request to pick the best candidate server so that the traffic is delivered as quickly as possible and the end user gets the best response time, the best experience. NGINX is configured through a simple set of flat text files, and the configuration structure for a load balancing policy is fairly straightforward. In this case, we have a simple server configured to listen for web traffic on port 80, and then all traffic is handled by the proxy pass directive, which passes it across to an upstream group. An upstream group is essentially a load balancing pool. It's a set of candidate servers that can respond to that request, and NGINX will apply a load balancing method to pick a server and forward the request to that one. In principle, very, very simple, and we can see it running in action with exactly this configuration. Here I have an example of a service that's load balanced using exactly that configuration with 4 web servers. And as I reload that page, you'll see that it flips between several of the web servers in that pool as a result of the round-robin load balancing algorithm. If we look at NGINX's status monitor, this is a capability that's just provided in NGINX Plus, then you can see the responses and how they're load balanced between the different servers. So since the software was restarted, each server's responded to 23 or 24 different requests. As we reload that a couple of times, you'll see those values increment. The more eagle-eyed of you will have noticed that there's something odd going on with this demonstration. As I reload that page, and it's load balanced between the different servers, you'd expect it in a round-robin fashion to cycle between web server 1, web server 2, web server 3, and web server 4. But it looks like requests are just being sent to 1 and 3. Load balancing is rarely as simple as it seems at first glance. And there's a strange effect going on here. NGINX provides you with the tools that you need to dive in and understand what is going on. In this case, the access log is a great tool to dump every single transaction and the data around that transaction. The server that responded, its response time, the headers it sent, and so on. If we look at the access log, you'll see here that NGINX is receiving 2 different requests. It's receiving a request for slash, which we sent through, followed immediately by a request for favicon.ico. This is a standard web image that most browsers request, and it gives you the little icon that's used when you bookmark the page or in the location toolbar of your web browser. So in fact, every time I reload that page, my web browser is sending 2 requests, and that's why it appears to be jumping from web server 1 to 3. you're not seeing the other requests that are interleaved in between. I've configured NGINX to log the identity of the upstream server that responded to the request. So if you look at the last entry in each of the log lines, you'll see that NGINX is, in fact, round-robining between web servers 1 through to 4. So logging is a really useful adjunct to load balancing to help you understand how your traffic is being managed and where it's being directed to. NGINX offers a range of different load balancing disciplines. Round robin is the default discipline. It rotates through the servers, picking one in turn. On the NGINX product, each individual worker process has a separate round robin table. When you run NGINX.Plus, there's an extension that enables a shared memory table for the load balancing data, and that allows it to round robin across all of the worker processes. Round robin is appropriate for simple websites where all of the traffic is likely to impose the same load on the back-end servers. And if your servers have different capacities, then you can apply weights to the round robin. Give each server a weight, and then NGINX will favor that server in accordance to the weight that it has. However, as I explained earlier on, one of the key goals of load balancing is to try and pick the best server for each request. If different requests can create different amounts of load on a server, then round robin doesn't always give you the best effect. In that case, least connections is an appropriate load balancing algorithm to use. And for each request, NGINX will pick the upstream server that at that instant is servicing the fewest transactions. So if a web server starts to pick up service requests that hit an application and they last for a long period of time, then the number of outstanding transactions will grow and NGINX will back off from sending it new transactions. This is a very good, stable way to distribute load when the effect on the web servers varies depending on the request. Again, least connections can be tuned using weights for individual servers, as can the final load balancing discipline, IP hash. IP hash does statistical load balancing. It takes the source IP of each request, hashes that, and then uses that to pick the target web server. Statistically, traffic should be evenly distributed between the web servers, providing they're coming from a wide and varying range of IP addresses. An IP hash has the nice side effect that all of the traffic from the same IP, source IP, is directed to the same target web server. This can be used to give you a basic session persistence effect. Later on in this presentation, we'll go through some more advanced capabilities for session persistence in NGINX Plus. A common requirement is to be able to manage the upstream pool, the group of servers that you're load balancing to. As you scale up, add more servers in. As you scale down, take the servers out. Maybe as you mark servers as down prior to maintenance or relight them when they're ready to be reused, then you need to modify the NGINX configuration. You can modify the configuration directly and then get NGINX to reload it with a reload command. There's no downtime incurred with that. NGINX loads the configuration in the background and then uses the new configuration for new transactions. It can be sometimes a little bit overwhelming to try and modify an entire NGINX configuration file, particularly if you're just looking for one subsection to add or remove a server entry. So NGINX allows you to create configuration files that include other files. Consequently, the simplest way to do this is to create a small, simple configuration file that represents just your upstream group, and then include that within the main NGINX config. You can even wrap different Unix permissions around that file if you have a separate process or a separate authority who's able to modify the load balancing config. This gives you a way to dynamically tune the weights, to dynamically change the up or down status of nodes within an upstream group. NGINX Plus introduces a new capability, on-the-fly reconfiguration. Using a privileged URL, you can modify the load balancing configuration for an upstream group on the fly without needing to reload any config. As a quick example, we can list the configuration for a group called backends, as so. We have 4 web servers in there. I can then mark one of those backends as down. I'll mark the last one as down, as so. So if we list the config now, you'll see that server.4 is marked as down. I can then restore it when necessary. So this gives you a very quick and easy way to make fast, transient, temporary changes to your NGINX config. For example, if you wanted to instrument the task of taking a server down or adding a new server into a load balance group. Sometimes you need more control over how traffic is routed. So far, we have just used some basic load balancing methods to try and pick the best server from a pool of equally capable servers. But there are examples where not all servers are equal, and you might want to favor one over another. For example, consider an application like WordPress. For the vast majority of traffic, you can safely load balance that across all of the servers in your load balanced farm. But an administrative user who's making configuration changes, perhaps he's writing a new article, he's uploading images for that article, and those images are stored on a local disk on the master server, and then they're rsync across to the slave servers. In that case, you might want to identify particular traffic and send it just to the master server. However, if the master server were to fail for any reason, you'd want to fall back to a backup server. This sort of scenario can very easily be met using NGINX and the backup servers capability. You can capture particular requests beginning WP admin, WP login, and pass them to a different upstream group. This upstream group can have a set of primary and backup servers in it. NGINX will always pick one of the primary servers unless none of them are available, at which point it then picks the backup servers. So your primary server could be the master for the file share. Files will be uploaded to the primary and then rsynced across to the secondary ones. As an alternative implementation, imagine that NGINX is load balancing traffic to servers in 2 different data centers, a local data center and a remote data center as a backup. You wouldn't want to send too much traffic to the remote data center when the local servers are running well, because the response time would be much greater. So you could tag all of the remote servers as backups. NGINX would only use them if none of the local servers are available. A related situation is one of session persistence. The session persistence capabilities I'm going to describe are just present in NGINX Plus. Although HTTP is intended to be a stateless protocol and easy to load balance, in reality, many applications carry state with them. They build up state, and that state is often stored locally. Consider a farm of web servers managing a shopping basket-like application. A user hits a link to add an item to his shopping basket, and that is stored locally on one of the web servers. When the user wants to browse the shopping basket or add more items, then that traffic needs to be routed to the same server because it is the one that has that state. Another example might be a more modern application that implements something like image editing. You have a farm of image editing servers and a web application that repeatedly makes callbacks to those image servers. You want to pin all those callbacks to the same image server so that you don't need to share that state across the farm. Or maybe it's an API-based application using HTTP but in a non-RESTful-like fashion, building up state and then accessing that state which is stored server-side. In all of these cases, you have the concept of a session, multiple web requests that reside in the same session. And you want to pin all of the requests in the same session to the same web server. NGINX provides a session persistence method to do this. The sticky cookie method identifies those requests and adds in a tracking cookie. Every time NGINX sees that tracking cookie, it knows to direct that request to the target server. Or the sticky write method applies a static rule looking at something from the request data, such as a cookie value, and mapping that statically to a target node. It's a really useful technique if you're running Java applications, because you can set the JVM route for each Java container to a different unique value on each server. That JVM route is appended to the JSessionID cookie or the JSessionID value in the URL, and then NGINX can pick that value out and map it back to the correct target server. So session persistence helps to avoid errors where state is lost. It also often helps to improve performance. By routing all of the transactions in the same session to the same target server, that server will have the state in local cache. It won't need to refer to a back-end database or query across the farm to find the master owner for that bit of data. And then finally, NGINX's load balancing can be used to deliver some pretty sophisticated and unusual solutions. I'll talk about A/B testing and application upgrades as two good illustrations of how to do that. A/B testing is a very, very common technique if you want to try several different implementations of a web service and see if they have a difference to your key metrics. Maybe your key metrics are performance, maybe they're ad click-through rates, maybe they're transactions, maybe there's something else. But it's very common that you may wish to try two or three different instances of the application to see which performs best. This is known as A/B testing. And the basic tenet behind A/B testing is that you partition your audience in some fashion which isn't weighted by their location or anything else, and you split that audience to different instances of the application, and then you monitor their behavior. For example, imagine you have an application that's running perfectly fine, but you have a candidate upgrade to the application that delivers better performance or better click-through rates or better stability or something else. Wouldn't it be great if you could partition your audience, send 90% to the existing application, but probe the new application with 5% of your audience to measure whether you are achieving the benefits that you're hoping? NGINX helps you achieve that. The split clients directive can be used to take a key, such as the user's source IP address, and map it to several different values. In this case, 95% of the time, the user's source address will be mapped to a string called backends. 5% of the time, it's mapped to an explicit IP address and port. This is the new test server. And that value is stored in the variable $servers. This sort of runtime configuration, where clauses are evaluated for each request, allows you to create some very, very sophisticated NGINX configurations. That $servers value can then be used in the proxy pass directive to identify either the upstream group or a specific server to route traffic to. You can make these sorts of decisions in your NGINX configuration in order to deliver precisely on this goal, taking 95% of your users and sending them to the existing application, and then farming off 5% for your test application. Another example is that of application upgrades. Imagine you have a web application running with a farm of servers, we'll call those backends A, and you wish to deploy a new instance of the application. Maybe it has new branding, new code, a new database, who knows? But the situation you want to avoid is that users who are in the middle of conducting a transaction against the old instance of the application should not be switched to the new instance of the application, because their transaction would fail, whether it be content that's broken or state that's lost. Every time a user comes in, you want to establish, do they have a session with a particular instance of the application? If so, load balance them to that instance. Otherwise, send them to the new instance of the application. That way, as user sessions complete and time out, they'll gradually be migrated from the old instance to the new instance, but without any downtime, without any loss of data, without any loss of sessions. You can achieve this very easily using the NGINX configuration, load balancing, and a tracking cookie that identifies the current upstream group for each session. The configuration looks something like this. I won't go through it in precise detail. I just want to explain that the bit of the configuration that's highlighted in bold is the only bit that you need to manage. With this configuration, all users will be routed towards backend B, but if you have a new upstream group that you add to your config, then you can seamlessly migrate your users to that upstream group just by changing that value in the configuration. These dozen lines of config are all you need to tag users with a cookie and then use that cookie to identify which instance of an application they're using. So, as we come to a close, we've looked at 3 case studies for load balancing. We've looked at basic load balancing with NGINX, using various algorithms, using the log files to track how the load balancing requests are distributed, looking at how you can manage the configuration, either by editing it directly or using the on-the-fly reconfig in NGINX Plus. We then looked at when you need more control, using backup load web servers for master and slave environments, and using session persistence, a feature in NGINX Plus. And finally, we've looked at a couple of advanced techniques that you can achieve by scripting your NGINX configuration to perform A/B testing or smooth and seamless migration of users from one application farm to another. I'd love to take any questions that you have at the end of the session, but first, leave you with some closing thoughts. 37% of the world's busiest websites use NGINX to deliver their web content and their web applications in a scalable, reliable, highly available fashion, using techniques like the load balancing that I've described in this presentation. If you'd like to find out more about the specific capabilities of NGINX and NGINX Plus, then look out the load balancing articles on our blog and the other information on the website. And for future webinars, check out the webinar list. We have a future set of webinars planned to go through other NGINX and NGINX Plus features over the next few weeks. Finally, the best way to try and experiment with this technology is to get hold of the software itself. The open source software, NGINX.org, or the commercial software with a free trial and evaluation from NGINX.com. Please get in touch if that interests you, and we'd love to set you up with an evaluation and help you through to achieve the evaluation goals. So with that, I'll take a brief pause. I'll thank you for your your attention, and I'll look and follow up with any questions that you want to submit to the Q&A panel.
And Owen, just to remind everyone, the Q&A panel is now located in the lower right-hand corner of your screen. Just enter your questions into the rectangular space at the bottom of that panel, and then click on the Submit button.
Thank you. So we've had a question through asking about the IP hash load balancing method, and how does that compare with session persistence in the case of routing to the same server. The IP hash method is entirely fixed. So when a request comes in from a source IP, then NGINX will calculate which is the target server by hashing that source IP, and then send that request to that target server. So all requests from the same source IP are sent to the same target server. In effect, it doesn't actually do load balancing. It just does request distribution. Session persistence is smarter. Session persistence can be applied just to particular URLs or particular transactions, and it's only turned on when it's needed. It works much better with the least connections or round-robin load balancing because the sessions can be evenly distributed across different machines. Okay, there's a question about denial of service attack and blocking IPs. Remember that NGINX is a fully fledged web server. It has all the capabilities you'd expect a web server to have. So you can easily put in configuration rules that will apply access control lists to IP addresses. You can also apply rate limits to transactions from IPs, and you can apply bandwidth limits to responses. So if you have a user, for example, who's trying to brute force the login for your website, you can give them a rate limit, so you can only make one login attempt a second, for example. Another question, can the load balancing server be load balanced as well, or is there only one load balancing server? This is a great chicken and egg problem. NGINX can load balance the backend servers, but how do you scale out and load balance NGINX itself? There are a few different solutions for that, and very happy to talk offline about techniques using keep-alive-D or corosync and pacemaker to achieve what you want. In almost every case we've encountered, single NGINXs are able to manage the volume of traffic that most sites take. A single NGINX on sufficiently powerful hardware can comfortably handle multiples of gigs of traffic. So the most common deployment is a master-slave configuration, where one NGINX is active, and then in the unlikely event that it should fail, then its IP is transferred across to the backup NGINX. If you'd like to find out about some more sophisticated approaches for that, then please get in touch offline. I'm very happy to talk. Okay, a question about load balancing for non-HTTP protocols, such as SIP. NGINX is an HTTP load balancer. So 95% of the world's TCP traffic is transported over HTTP. That's exactly the sort of traffic that NGINX can pick apart, inspect, optimize, multiplex the keep-alive connections, and handle with aplomb. At present, we don't have capabilities for other protocols such as SIP. We can load balance a range of mail protocols, SMTP, POP, and IMAP. Check out the documentation on nginx.org and the deployment guides for more details. How does NGINX detect errors in applications and route away from them? So, a very good question, and that will be one of the areas that we'll cover in a following webinar. So, in short, NGINX and NGINX Plus have a couple of different means to detect whether a server has failed. NGINX inspects the responses from upstream servers when it sends them a request. If the response times out, or if it contains an HTTP error, a 500 error, and you can configure what makes up an error, then NGINX will retry that request against a different server in the group. And if the server consistently fails, then NGINX will stop trying requests against it and eventually start again. NGINX Plus adds some additional health monitoring capabilities. You can configure NGINX Plus with a set of synthetic transactions. It will run those against the upstream servers asynchronously. To probe them, maybe the transaction is going to hit a PHP script that's internal only, that does some internal consistency checks, make sure that the database is still up, that the shared file system is working. If those scripts or those requests return an error, and again, you can configure what constitutes an error, then NGINX will mark that server as down. So those capabilities in NGINX Plus give you a wider way to detect errors in your application and route traffic away from it without having to probe the application for real traffic. We'll go through that in a lot more detail in a future webinar. So, folks, thank you very much. It's been a great webinar. I greatly appreciate your patience and your participation in this. A good set of questions. If you have any further questions, or if you want to try the software out, then you know where to find us, nginx.com, and I look forward to speaking with some of you shortly. Thank you.
And ladies and gentlemen, this does conclude your session for today. I want to thank everyone for joining and hope you found it informative. And at this time, you may now disconnect and enjoy the rest of your day.